Last time we introduced the Thompson sampling algorithm. This time we are going to analyze its performance. We are going to study how its regret grows over time. And we will introduce some preliminary ideas that are needed for that analysis. So I'm going to share screen with you now. Okay. So we'll begin the analysis of the regret of Thompson sampling in this lecture. Let me begin by recalling the algorithm itself. So we are studying it in the context of a bandit with k Bernoulli arms. This means that the reward on each arm is a 0, 1 valued random variable. When you play the arm, you get a success or a reward of 1 with probability mu sub I for the ith arm. And with probability 1 minus mu I, you get a reward of 0, which you can think of as a failure. And these success probabilities mu 1 through mu k are unknown. The goal is to learn them at the same time as gaining rewards from playing those arms. And the trade-off is between exploring in order to find the best arm and exploiting what we currently think is the best arm. Thompson's approach to this problem was to assign a prior distribution for each of the unknown parameters, mu sub I, and we'll follow him in assuming that these are independent beta priors with parameter 1, 1. Let me remind you again of the Bayesian approach to estimation. So we have these parameters which we don't know, and we represent our lack of knowledge of them by assigning them a probability distribution. We say we don't know what the value is, but each of these mu I is a number between 0 and 1. It's a success probability. So we will put down a density on the interval 0, 1 and use it to represent our prior uncertainty about this parameter. The beta 1, 1 distribution happens to be the same as the uniform distribution on 0, 1. So effectively, we are saying that since we know nothing whatsoever about these parameters, let's assume that they are equally likely to take any value between 0 and 1, and so let's assign them a uniform distribution. Okay, so these are the priors we start with. Then what do? We draw samples from these priors, independent samples. So the samples theta sub I you can think of as a guess of mu I. It's not a fixed number. It's not the mean of the prior distribution or its median or something else. It's random, and it reflects the uncertainty we have about the true value. So we make a random guess at each of the mu i's. And then we do the natural thing. We play the arm for which the guessed value is the biggest, because if we trust our guesses, that's what we think is the best arm. So we play the arm with the largest value of theta I. If we had 3 arms and the values theta I that we drew were 0.3, 0.62, and 0.49, then we'd play arm 2, which had a value of 0.62. Okay, so we play a certain arm, and then we observe the reward on that arm, which is either 0 or 1, success or a failure. And based on that, we compute the posterior for the parameter mu I, for the success probability on that arm. And for all the other arms, we observe nothing. You can only observe rewards on the arm you actually play. Since we have no other information on the other arms, we don't update our beliefs about them. So the posteriors for those arms are the same as the prior distribution. The uncertainty has not changed in any way. Okay, and finally, we set the priors at the start of the next round to be the posteriors computed at the end of the current round. So that's the algorithm. So pause here a moment to make sure you understand the algorithm. Okay, next, before we move on, let's get some intuition about why we think this algorithm should work in the long run, should do something sensible in the long run. Assuming you explore enough, assuming you play each arm a large number of times in the long run, then what do you expect the posterior to look like after you have played an arm many times? So suppose the true value of mu, the success probability on a certain arm, is 0.4. And say you have played it 100 times, then you can expect that the proportion of successes you observe is something close to 0.4. So maybe you observe 35 successes and 65 failures. So if you were to just estimate the mean, then mu hat would be 0.35. And in the UCB algorithm, we computed mu hat, and then we added a certain amount of random we added a correction to account for our uncertainty about the parameter and used that to choose which arm to play. Here, our uncertainty is represented by the posterior distribution for the parameter mu. And so we take our uncertainty into account by sampling from the posterior in order to decide which arm to play. So what do the posteriors look like after the arm has been played many times? So if the arm has been played 100 times, and we observe 35 successes, then the posterior distribution is going to be beta with parameters 1 plus 35 and 1 plus 65. So this is what we showed earlier when we showed that the beta is a conjugate prior, meaning that the posterior distribution also remains a beta random variable. Okay. And what does a beta distribution with parameters 36 and 66, or some large parameters, look like? It looks very concentrated around its mean value, which is alpha over alpha plus beta. So in this case, it's that ratio is approximately 0.35, very close to 0.35. And so the posterior after 100 plays of this arm is concentrated very close to 0.35, very close to the true value 0.4. And as we play it more times, it will get closer and closer to 0.4 and become more and more concentrated. In that sense, we learn the true parameter as we play the arm often enough. But even though it concentrates close to that value, it never concentrates fully on that value, and it's fully spread out over the entire interval, not to 1. Meaning that when you sample it, there's a small chance that you get values very close to 0 or very close to 1. And this is enough to ensure that every arm does get explored eventually, no matter how many times it's, no matter how low its parameter appears to be. So just like the UCB algorithm, the Thompson sampling algorithm has a built-in mechanism to account for uncertainty and thus to ensure that we don't stop exploring arms. And this is important because if we only explode each arm a bounded number of times, let's say 100 times, then a run of bad luck on the first 100 place of this arm could lead us to ignore that arm in future, even though it happened to be the best. Okay, so that was just a review of the algorithm. And now we are going to move on to the analysis. So what's the question we want to address? We want to obtain some bounds on the regret of the Thompson sampling algorithm. In particular, we want to know if it's optimal, or at least if it has the optimal scaling with time. With the UCB algorithm, we showed that the regret scales like some multiple of log t. So the regret up to time t grows only logarithmically in t. And we also quoted a result of Lai and Robbins, which showed that no algorithm can do better, that for any algorithm, the regret should grow at least as fast as some other constant times log t. And the algorithm is optimal if these constants match. UCB isn't quite optimal in that sense. It's close to optimal, but not exactly so. But it does achieve the logarithmic scaling. And it turns out that the same is true of Thompson sampling. It does achieve the logarithmic scaling. As far as I'm aware, we don't know whether it does achieve the exact constant in front, the best constant in front, but we do have some bounds on it. Here's a theorem that states the result for multi-arm bandit with two Bernoulli arms. So let's say the mean rewards are mu1 and mu2, and as usual, we'll assume that mu1 is bigger than mu2, and there's no loss of generality in this assumption. This is just a labeling of the arms. We are not assuming that the player knows the labeling, so they don't know which arm is better. Okay, and we denote this difference by delta. A big value of delta means that you incur a big regret whenever you play the second arm, but the arms are easily distinguishable, so over time you learn its worth faster. A small value of delta means that you incur a small regret each time, but the arms are hard to tell apart, and so you might end up playing the suboptimal arm more often in the long run. The result, the theorem states that the regret of Thompson sampling is bounded by some constant times log t over delta plus another constant. And this latter constant may depend on delta, but should not depend on t. And the structure of this regret is exactly the same as for UCB. There too, we had a certain constant times log t over delta plus some other constant which depends on delta. So essentially, our bounds for Thompson sampling are similar to those for UCB, maybe a bit worse than those for UCB. But in experiments, its performance actually turns out to be somewhat better than UCB. So that's just saying that our analysis may not have picked up the exact constant in front. We only have bounds on it. But essentially, we are in the right ballpark because we do capture the logarithmic growth in t, and we do capture the 1 over delta dependence on or 1 over the KL divergence dependence on the on how dissimilar the two arms are. Okay, we are not going to prove this theorem. It's a full proof is pretty difficult, but we are going to go over some of the ideas that play an important role in the proof. And we'll do it in this lecture and the next two lectures. Okay, so our approach to analyzing the Thompson sampling algorithm is going to involve bounding the probability that if we sample a beta random variable, the sample lies far from the mean value of the random variable. So we already argued that after we observe an arm for a large number of times, the posterior distribution concentrates around the true mean reward of that arm. So we need to bound two things. We need to bound how far the estimate is from the true mean. And we also want to bound how much a sample from that beta deviates from that estimate and hence from the true mean. Okay, so we need bounds on deviations of a beta random variable from its mean. And we are going to, rather than calculate that directly, we are going to approach it indirectly via the CDF of a binomial distribution. So we are going to relate the distribution function of a beta random variable with that of a binomial random variable. And this relation we derive will only work for beta distributions with integer parameters. So that is a limitation of this result, but since we start with beta priors with integer parameters, our posteriors will also always have integer parameters. So this limitation doesn't affect us. Okay, and the way we'll use that to bound the probability of deviations of the beta is in terms of those for a binomial for which we know we can use Hufting's inequality. So let me state this relation as the following lemma. So we have a parameter p between 0 and 1 and a beta random variable x whose beta distribution is parameterized by alpha and beta. And these we assume to be natural numbers. This notation n plus 1 is to make it clear that we are starting counting the natural numbers from 1 rather than from 0. So alpha and beta take values 1, 2, 3, and so on. Recall that the parameters of a beta distribution always have to be strictly positive. So alpha and beta have to be bigger than 0 for this distribution to be well defined. And so if we restrict them to natural numbers, we can't allow them to have the value 0, only values starting from 1. Okay, that's x. And then y is a binomial random variable with parameters alpha plus beta minus 1. That's the number of trials for the binomial. And p is the success probability. P is this other number we chose between 0 and 1. So x and y are related through their parameters in this way. Then the assertion is that the probability that the beta random variable x takes a value bigger than p is exactly the same as the probability that the binomial random variable y takes a value less than or equal to alpha minus 1. Okay. And this is true for every possible p between 0 and 1. In other words, we have specified the CDF or the complementary CDF of the beta random variable evaluated at any p in terms of the CDF of a binomial random variable which has the same p as one of its parameters. So that's the relation between these two distribution functions. Okay, so now we are going to turn to the proof of this lemma. You could prove this directly from the definition just by using the formulas for the beta and the binomial and by direct calculation. And if any of you would like to try that, I welcome you to do so. That is possible to do. But we are going to take an indirect approach which allows us to avoid calculations altogether. And that approach is going to use properties of Poisson processes. Okay. So this is the first time I'm mentioning Poisson processes in the course. You should hopefully all have seen these already in probability 2, which is a prerequisite for this unit. But in case you haven't, or in case you have but don't remember it very well, I'll go over it again. But if you have not seen Poisson processes before, you should definitely pick up a textbook and familiarize yourselves with them better. It is important. And I'm only going to do a very quick overview. Okay, so what's a Poisson process? It's a random process in continuous time. So it's indexed by t, which takes values in the positive real numbers. And nt is going to denote our Poisson process. So it's a random variable for each possible value of t. And it's going to be a counting process, meaning that its value at any time is a natural number, a counting number. By convention, it starts at 0 and it counts the number of occurrences of some event we are interested in up to time t. So it may be, so you may be driving along a road and you may be counting the number of stop signs you see up to time t. So the count starts at 0 and every time you see a stop sign, the count goes up by 1. So it's always integer valued and it's never decreasing over time. So that's a counting process. Such a counting process is called a Poisson process if one of the following two things is true, and these are equivalent. The first tells us what these random variables nt look like for different values of t. So the process has independent increments. What that says is that if we look at the process from time 0 to s, then what happens between time s and t, the increment nt minus ns over that subsequent interval is independent of whatever happened before that time. So nt minus ns is independent of the process up to time s. Okay. So firstly, there's that independence. And secondly, we also specify what the distribution of this random variable is. It's a Poisson random variable with parameter. So the parameter of a Poisson random variable is the same as its mean. And the parameter is lambda times t minus s. So the mean of the Poisson is proportional to the width of the interval t minus s, with proportionality constant lambda, which is a parameter of the process. So the parameter lambda is called the rate or the intensity of this Poisson process. Okay, so let me repeat that again. So Poisson process is a counting process with the following property. The counts over disjoint intervals, the number of events we see over disjoint intervals are mutually independent. And also the count over an interval is a Poisson random variable with parameter lambda times the size of the interval. Okay, so that's one way to describe the counting process. The other way is in terms of the times between when the counts increase. So nt starts at 0. We can look at the time t1 when it first goes up to 1, or in terms of our driving analogy, when we see the first stop sign. And then we look at the time between t1 and t2 when the count again goes up, or between t2 and t3 when the count goes up once more. And the claim is that these times T1, T2 minus T1, T3 minus T2, and so on, the gaps between successive increments. These are all independent, identically distributed exponential random variables, and the intensity of the Poisson process is the parameter of this exponential. Okay, notice that this description tells us one more thing. It tells us that the process cannot have multiple jumps. It increases by at most one at a time. And the reason for that is to have a multiple jump, you must have an increment time which is 0. And the exponential distribution has no atom at 0. The probability it takes the value 0 is 0, or any specific value is 0. Finally, let me also remind you that a Poisson random variable is discrete. It takes integer values. This counts the number of points and number of jumps of the Poisson process, which is an integer. The exponential random variable is continuous. It takes real numbered values, and this measures the time interval between jumps. Okay. And these are two completely equivalent descriptions of the Poisson process. Okay, so maybe a picture will help. So here we've drawn a sample path of a Poisson process. Time is along the x-axis and the count is along the y-axis. The process starts with the value 0. After some random time, which is exponentially distributed with parameter lambda, it jumps to 1. The count increases to 1. After another independent x lambda time, it increases to 2. Yet again, after yet another x lambda time, to 3, to 4, and so on. So that's what a sample path of the Poisson process looks like. Another way to say this is if we pick 2 times s here and t here, the increment between s and t. So in this sample path, there have been 2 jumps between s and t. So t is 3 and s is 1. So the difference is 2. This increment is a Poisson random variable with parameter lambda times the size of the interval st, lambda times t minus s. And also the number of jumps in this interval are entirely independent of what happened before time s. So they are independent of the past. That's the other way to describe the Poisson process. Okay, so why have we introduced this process? We've done so because we are going to use the following property of the Poisson process in the proof. I'm not going to prove this property, but it's not hard to prove. Okay, so let Nt be a Poisson process with some intensity lambda, and the result's not going to depend on the value of the intensity. It's arbitrary, it drops out. Okay, so let's fix a time tau and a natural number n. So we are going to condition on the Poisson process Nt having exactly n jumps up to time tau. I tell you that the number of jumps up to time tau is n. And I want to know where these jumps were. I haven't observed when the jumps took place. All I know is that there are n of them up to time tau. And I want to know what the distribution is of the times at which these jumps occurred. And it turns out that the jumps were equally likely to occur anywhere in this interval. So they were equally likely to occur anywhere between 0 and tau, and the times at which the n different jumps occurred are all independent of each other, mutually independent. So in other times, if we take the jump times t1, t2 up to tn, in our notation, these are ordered in increasing order. But if we take the set and jumble them up. So if we look at the unordered jump times, then these have exactly the same joint distribution as if we had sampled n independent uniform random variables between naught and tau. So if we take a set of n independent uniform random variables, this set has the same distribution as this set. By thinking of the sets, I'm ignoring the ordering within the elements of the set. Okay. So these two sets have exactly the same distribution, and that's that of IID uniform random variables between naught and tau. So this is an important property of the Poisson process. So just to repeat that, if I tell you the total number of jumps in an interval, then the locations of those jumps are independent and uniformly distributed. Okay, so now we'll use this property to prove lemma 1, which related the distributions of beta and binomial random variables. So let's take x to be our beta random variable with parameters alpha and beta, y to be our binomial with these parameters alpha plus beta minus 1, and p where we are given alpha and beta in the natural numbers and p between 0 and 1. So these are our two random variables of interest. Now recall that we showed how a beta random variable is related to gamma random variables, and we are going to use that now. So we can express a beta random variable x as this ratio v over v plus w, where v is gamma with shape parameter alpha, which is the first parameter of x, and scale parameter 1. W is also a gamma random variable with shape parameter beta, the second parameter of x, and scale parameter 1. So the scale parameters of these two things have to be the same. They don't have to be 1, it's not important, but they have to be the same. And finally, the random variables v and w are independent. Okay. So we can construct a beta random variable this way in terms of gamma random variables. And by construct, I mean if you wanted to simulate x and I gave you a computer program which could simulate from gamma random variables, you could use that to simulate from beta random variables in this way. Okay, so that's how we express our beta random variable. Now, next, I'm going to express the random variables v and w, the gamma random variables. I'm going to relate them to a Poisson process. And this is how we do this. So let's take nt to be a Poisson process whose intensity lambda is equal to 1. That's what I mean by unit intensity. Okay, so nt is a Poisson process with intensity 1. What does that mean? It means that the time t1 of the first jump is exponentially distributed with parameter 1. Then t2 minus t1, the time until the next jump, is an independent exponential with parameter 1. And similarly for t3 minus t2, t4 minus t3, and so on. All the successive gaps between jump times are IID exponential 1 random variables. So if T alpha is the time to the alpha jump, so that's the sum of alpha IID exponential random variables. And we know what that distribution is. That's a gamma with shape parameter alpha and scale parameter 1. And if you've forgotten that, take the time to remind yourself of this fact. So if alpha is 1, the gamma is the same as the exponential. If alpha is some other natural number, then gamma is the sum of alpha independent exponentials with whatever scale parameter, fixed scale parameter you're given. Okay, so T alpha has the same distribution as V. What about T alpha plus beta minus T alpha? So this is the time for beta additional increments starting at time T alpha. So we start at T alpha and we look at how long it takes for there to be beta more jumps in the Poisson process. And since each of those jumps takes exponential 1 time, this is the sum of beta independent exponential 1 random variables. And so that has a gamma distribution with shape parameter beta and scale parameter 1. That's the distribution of W. Okay. So T alpha plus beta minus T alpha has the same distribution as W. And finally, V and W are independent because the Poisson process has independent increments. What happened up to time T alpha is independent of what happens after time T alpha. Okay, so we have expressed V and W in terms of the Poisson process. So we have expressed X in terms of the Poisson process, N and T. So X has the same distribution as T alpha divided by T alpha plus beta. And this event we are interested in, that X is bigger than P, is exactly the same as the event that T alpha is at least as big as P times T of alpha plus beta. Okay. So in terms of the Poisson process, the event that X is bigger than P is the same as the event that the time up to the alpha jump of the Poisson process is at least as big as a fraction P of the time up to the alpha plus beta jump. Okay, take a moment to make sure you understand this. Okay, so we've expressed a beta random variable in terms of the Poisson process. We've related these two. Now we are going to relate our binomial random variable y to the same Poisson process. How is y related to NT? Okay. So by definition, the number of jumps, the alpha plus beta jump of the process NT occurs at time T of alpha plus beta. That's the definition of T of alpha plus beta. So if we look at the open interval up to this time, there are alpha plus beta minus 1 jumps in that interval because the alpha plus beta jump happens at this time. And also notice that we said you can't have multiple jumps. So at this final time, you can only have exactly 1 jump. So that leaves out 1 jump, and the remaining alpha plus beta minus 1 jumps happen in this open interval. Okay, next, by the fact about Poisson processes we stated earlier, if I condition on the total number of jumps in this interval, when exactly these jumps happened are independent and uniformly distributed random variables. So these alpha plus beta minus 1 jumps are uniformly distributed within this interval. It doesn't matter whether it's open or closed now, because for the uniform random variables, they have 0 probability of falling at 1 exact value. So it's the same whether it's the open or closed interval. Okay, and there are alpha plus beta minus 1 jumps scattered independently and uniformly here. So if we ask how many jumps fall within this smaller interval, not to P times T alpha plus beta, well, each of these jumps is uniformly distributed. So it has probability P of falling in this interval, which is a fraction P of the total width of the interval where they are distributed. And they are also independent. So each jump falls in this interval with probability P, and it's independent of the other jumps. And that's exactly the setting for a binomial random variable. So you have alpha plus beta minus 1 jumps. This is the number of trials. P is the success probability that the jump falls within that interval. And the number of successes in independent trials has a binomial distribution. Okay, so this is the distribution of the random variable y. So what have we shown? We've shown that the event that T alpha is bigger than P times T alpha plus beta. The event that the number of jumps of the Poisson process in this interval is smaller than alpha, meaning that it's at most alpha minus 1, is the same as the probability that this binomial random variable takes a value smaller than alpha, smaller or equal to alpha minus 1, because this binomial random variable has the exact same distribution as the number of jumps in this interval, not to pt alpha plus beta. Okay, so saying T alpha is the time up to the alpha jump. So, okay, maybe now's a good time to draw this as a picture. And let me stop sharing the screen and try using a whiteboard. Okay, so we have this time, this random time T alpha plus beta here. I've marked this. We are given a parameter P, and we are looking at this other time, P times T alpha plus beta. And we have a Poisson process which has increments at random after random x1 times. Okay, and T alpha plus beta is the time of the alpha plus beta jump of this Poisson process. And then we are asking whether at least alpha jumps have happened by this time, P times T of alpha plus beta. No, sorry, that's not what we are asking. We are asking whether T alpha is bigger than this time. The time to the alpha jump is bigger than this time. If the time to the alpha jump is bigger, then there can be at most alpha minus 1 jumps in this interval. Okay, so the event that T alpha is bigger than this is the same as the event that there are at most alpha minus 1 jumps in this interval. And that was related to our binomial random variable. So let me go back to sharing the other screen. Okay, so that's how the beta distribution is related to the binomial distribution. Okay, so and that completes the proof of our lemma. Okay, so we'll stop here this time, and next time we are going to use this fact to analyze the regret of the Thompson sampling algorithm.